So let's look at a mechanism for the formation of a hemiacetal. One thing to keep in mind, a hemiacetal has a carbon bonded to an OH group and an OR group. And it's usually the intermediate step to the formation of an acetal. Hemiacetals tend to be less stable than acetals and aren't usually final products, with the exception of cyclic hemiacetals, kind of what we see here. And so when we look at the mechanism of these, they're typically done in acidic conditions. And if you saw my video on hydrate formations, in acidic conditions, the first step is usually the protonation of the carbonyl to make it more electrophilic. So if I had my sulfuric acid here, I'm going to draw it out the long way, but there's shorthand ways to draw it as well. But if I have my sulfuric acid, the first step is going to be the protonation of that carbonyl. So the carbonyl is going to accept a hydrogen from the sulfuric acid, and what we're going to get in return is this protonated carbonyl. The purpose of doing that is it's going to give us a more electrophilic carbonyl so that our nucleophile can attack. Now, when we do form acetals and hemiacetals, they can be intermolecular or intramolecular. Intramolecular would be if I didn't have an alcohol here, instead I added a separate alcohol that would then add to my carbonyl. That would be intermolecular. But sometimes you have an alcohol present in your molecule already, and we can get an intramolecular reaction, which results in the formation of a ring, because that alcohol within the molecule will add to the carbonyl, and we form this cyclic structure. Now, when my nucleophile adds, I need to break the bond between carbon and oxygen here to go down to a single bond. And we would get our cyclic structure along with um, our hemiacetal sort of piece, but we're not quite done yet because as you can see in the structure, we still have that hydrogen from our alcohol attached. The last step is just a proton transfer to get rid of that hydrogen. Now, typically, your alcohol is going to be what does the proton transfer. If you have an intermolecular reaction, for example, the methanol or ethanol or whatever alcohol would remove that hydrogen. This one gets a little difficult to draw because you have to redraw the entire piece again, and it's kind of large for this. But here we go. We have our alcohol. It's going to deprotonate our hemiacetal piece here, and we'd get to our final product. So the steps in a nutshell when you form a hemiacetal is you start with a proton transfer. That's going to activate the carbonyl by protonating it, making it more electrophilic. You then have your nucleophilic attack of the alcohol. And once you form that bond, you essentially have your hemiacetal, but it has an extra proton that we need to remove via proton transfer. And here I showed the alcohol removing that proton. Again, there's other things that could potentially remove that. Technically, you could have the carbonyl remove that hydrogen, and it kind of just starts a cyclic sort of process where now you get to this part again, and then that can undergo cyclization and then form your hemiacetal a second time. But usually, the alcohol of that's in the solution is going to do this proton transfer step at the end.